All right. Now we have seen fully connected artificial neural networks with sigmoid activation function in the last layer, so for binary classification, and we have seen neural networks with a linear activation function in the last layer, so for regression, right? So what about multi-class classification? Now, as an example, so let us think of this scenario where we want to do an image recognition with 5 possible classes: no face, bare face, face shield, face mask, and both shield and mask at the same time, right? Now, so the input of our algorithm is going to be an image. And by the way, so the image is just the collection of pixels. And let's say, hypothetically, if we have an image, say, of size, let's say 500 by 400 pixels. So it means that, so we have 500 by 400 pixels, and every pixel has 3 color channels, so red, green, and blue. So every pixel is represented by 3 numbers between 0 and 225, I think. But it doesn't matter. So you can think of them as numbers between 0 and 1, right? So there are 3 numbers. So it's going to be 500 by 400 by 3, and this is 600,000, right? So which means that our multi-class classification, if we work with images 500 by 400, which is actually not very large, then we will have, so the input size is going to be 600,000. So what do we do in this case? Now, our raw response variable is one of the 5 classes. So we are going to convert it to a vector response variable, so whose entries are zeros and ones, right? So 1 is in the position corresponding to the class that observation actually belongs to, right? So if we have 1 on position 4, then 4th class is face mask. So it means that it indicates that the person on the ith photograph is wearing a face mask. So then our model's prediction should be a probability vector, right? So it means that, or a probability distribution. So if we have 5 numbers, P1, P2, and so on, P5, then these numbers should be between 0 and 1. And the sum of these 5 numbers should be 1. But before applying the activation function in the output layer, right? So the activation in the output layer is AL. But before applying it, so this AL is our activation function F applied to ZL. And ZL is the result of the matrix transformation to the input of the previous layer, of the layer L-1. And this ZL can be an arbitrary vector. And since in the end we want to get a 5-dimensional vector, right? So it means that it can be an arbitrary 5-dimensional vector. So 5-dimensional vector. But it can be anything, right? So it can have positive, negative numbers, so that there is no restriction here. Now, what we could do, of course, we could just, instead of coming up with a clever activation function, we could just look at this vector and say, okay, the largest entry here is entry number 4. So the largest entry is entry 4. Entry 4 is the largest. So which means that we are going to classify to predict the face mask. So entry 4 corresponds to face mask. Entry 3 corresponds to face shield, or whatever. But what is wrong with this approach? So the problem is that we could do it. So we could just cook up the final prediction out of this Z vector, but this final prediction would not be a differentiable function of the input, right? So we would not be able to train our neural network using gradient descent because, well, it simply is not differentiable. And it would not give us class probabilities, which sometimes is very convenient to have, because class probabilities, they show how confident the model is in its predictions, right? So, and very often, I don't know if our model is very confident, then we just trust it. But if our model is not very confident, so if, I don't know, if it predicts that, okay, so the probability that this person is wearing a face mask is, I don't know, 0.6 rather than 0.99, and then we could probably, interfere as a human and see what's going on there. So it is convenient to have class probabilities, right? So we need to convert an arbitrary vector in R5 to a probability vector, and the softmax function does just that. So the kind of the default choice is this softmax function. So let me just verify that the softmax function actually does that. Right? So I'm going to first notice that the softmax, the numerator is e to the zi, so it's positive. The denominator is the sum of e to the z, so this again is positive. So the softmax function is positive, right? So the every entry of the softmax function is positive. Now let me verify that if I take the sum of entries of the softmax function, softmax of z I. So here z is a k-dimensional vector, and softmax of that is also a k-dimensional vector. So let me add them together to see whether I will get one indeed, right? So now what I'm going to get now, I'm going to just insert the definition of the softmax function. So I'm going to get e to the zi divided by the sum over j from 1 to k e to the zj. And this sum is taken by I from 1 to k. Well, but notice that this term here does not depend on I, so which means we can just take it out. So this is going to be 1 over the sum over j. So I will I will omit the limits of summation. So e to the zj times the sum of by I of e to the zi. Right, but these two sums are actually equal. I mean, so they look different, but it's exactly the same sum. It's just that one is in one of them, so we use I as the notation for the index of summation. In the other one, we use j as the notation for the index of summation. But of course, it doesn't matter, right? Whether you denote it by I, j, I don't know, k, sigma, or whatever. So it's still the same thing. So this is just really the sum of e to the zi divided by the same thing. So, and this is 1. Okay, so correct. So every entry of my softmax, of the output of the softmax function is positive, and the sum of the entries is 1. So which means it is correct. So it is actually, it is a function from all vectors in R5 to the probability vectors in R5. And so, and this softmax function, it helps us to come up with a artificial neural network that is going to do a multi-class classification, right? So for a k-class classification, so let me by h theta of xi to denote the vector whose kth entry is the probability that is the estimated probability that yi hat belongs to class k, right? So the corresponding loss function is the categorical cross entropy. So the familiar one, so it's just that notice that whatever is here is the output of our model. Model's output for the ith training observation. Okay, this was multi-class classification, but by contrast, sometimes we want to have a possibility of predicting more than one class for a given test observation. So the simplest example probably is photographs. So if we want to recognize faces on photographs, then the same photograph may have several different faces, right? So for every person in our database, we want to predict the absence or presence of that person on a given photograph, right? So if we have, I don't know, Alice, Bob, whoever, so then for a given photograph, so we will output the probability that Alice is there, the probability that Bob is there, the probability that Caitlin is there, and so on and so forth, right? And we're going to have a lot of probabilities, but they may not add up to 1 because Alice and Bob can be on the same photograph. So, and for this scenario, we are going to have a binary sigmoid neuron associated with every person in our database. So we are going to have a multidimensional output, but the activation function is not going to be a softmax, it's going to be a sigmoid activation function. Only instead of just one-dimensional output, we will have a multidimensional output, right? So, but this is important, right? So for a situation where so every test observation or every training observation may have several classes, then we are going to have several sigmoid neurons. If it is just precisely one out of k classes, then it's going to be softmax instead.